In this presentation, I'm going to show you the tailored pavement management system procedures and geographic information system tools implemented in several small road administrations in central Italy. The use of systematic process based on pavement management system can help the road administration agencies to make maintenance rational, objective and cost-effective, even if the PMS principles don't change moving from different contexts. Small administrations need of customized tools that substantially differs from those adopted by highway and airfield administrations. Since small road authorities generally manage a wide and heterogeneous road network with limited budget, human resources and tools, in this context the implementation of PMS with GIS can give great benefits due to the representation of road data on maps. Moreover, customized GIS tools can be created to increase data collection, analysis processes and maintenance planning assessments. The research program aims to establish a tailored and sustainable PMS for several small road administrations, which support and standardize survey activities, ranking maintenance priorities, and identify the cost-effective strategies. To obtain understandable output results, such as thematic maps, to create a GIS database of road information, to implement customized GIS-based tools for design analysis and multi-year planning, and finally to define technical methods, design documents, and quality control procedures. The tailored pavement management system, developed for several small road administrations in central Italy, was designed as a circular sequence of connected phases, in which every activity outcome is the starting point for the following one. On the left of this slide you can see the functional phases, while on the right the activities to be performed in each phase respectively. In detail, the process identifies two operative levels, network and project level. The first one, highlighted in red in this slide, is relating to the periodical monitoring of pavement condition and the evolution over time of pavement distresses on the entire road network. The areas with low performance or conditions are ranked in a priority maintenance list according to technical limits. While at the project level is performed the design of maintenance applied to the priority areas. The technical and economical evaluation were performed using long-term prediction models. And finally, a strategic index was defined to compare different maintenance planning strategies. The road network was implemented on GIS database and divided into networks and road types, then in homogeneous sections with same characteristics, and finally in inspection units. The inspection units are wide as the road lane and have a maximum length of 0.5 km for urban roads and 1 km for suburban roads. Each road sections and inspection units were identified with a unique alphanumerical code to avoid misleading identifications in the GIS database. On the left of this slide, you can see the road network classification according to hierarchy and road function, while on the right you can see the road type classification by the urban and suburban context. For the evaluation of pavement roughness, the International Roughness Index (IRI) was measured on specific routes using a selected application for smartphones, while for the evaluation of pavement condition, a rating system was defined considering standardized visual inspection method. The Pavement Condition Index (PCI) was calculated on several pavement segments to create a reference scale and address the classification of inspection units by comparison. Also, road emergency on restricted areas can be reported using a GIS mobile service. The Priority Index (PI) was defined to establish a maintenance priority rating and scheduling of maintenance works. In detail, the priority index was defined as a number ranging from 100 to 0, where 100 means the maximum priority, while 0 means no repair or preventive maintenance. The priority index considers the following technical factors: estimated or measured pavement condition and roughness, traffic level based on average daily traffic values, road network hierarchy and function factors based on network types and road function classification, strategic function factors based on commercial or tourist roadways and places of public interest, and finally, historical maintenance and rehabilitation factors based on annual costs of previous maintenance works. Note that the priority index is calculated if the PCI or IRI values exceed the respective safety threshold, PCI lower than 55 and IRI equal or greater to 6 for primary roads, and IRI equal or greater to 10 for local and secondary roads with operating speed lower than 50 km per hour. All the priority areas have to be investigated at the project level to identify the specific maintenance strategies, considering pavement distresses and their severity degree. As shown in this slide, a catalog for structural design was defined to standardize maintenance repairs and rehabilitation works. The following deep and intermediate repairs can be used for roads with average daily traffic lower than 5,000 vehicles per lane and commercial vehicles lower than 10% of traffic volume. All the project information, like extension, materials, and type of maintenance works, were implemented on GIS database. Long-term maintenance planning was performed using projection models for estimating the evolution of pavement condition over time. In detail, specific deterioration models were defined for each type of standardized maintenance repairs and existing road pavements. The predicted PCI values of road inspection units were calculated using exponential laws relating to the current pavement condition, traffic volumes, percentage of commercial vehicles, and repair methods. In this slide, it's shown an example of long-term maintenance planning in which the pavement condition of road network, including repairs, are implemented using a time sequence of thematic maps. At first, in picture A, the pavement condition rating was displayed, and then in picture B, the priority index were calculated considering the road inventory information. Then, as shown in picture C and D, the future pavement conditions were calculated using customized scripts on GIS database to implement the deterioration models for each type of maintenance repairs. The comparison between alternative maintenance strategies was performed using a strategic index, SI. The strategic index allows to estimate the overall pavement condition level of road network over time, considering the predictive condition models to calculate expected PCI and PI values for each inspection unit and repairs, according to the following equation. Note that low value of strategic index means a good global condition, because the priority index values are lower for good condition. In this slide, it's shown an example of strategic index results for two alternative maintenance strategies, considering the same budget and range of time. Scenario 2 considers the use of superficial repairs to cover an extended road length, but run out quickly after just the fourth year, while Scenario 1 combines superficial and deep maintenance repairs to allow together long-lasting benefits. In conclusion, the research project has allowed to create an overall scheme of action to be performed using specific tools and reference documents for an efficient and sustainable PMS for small administrations. The use of GIS tools was useful for the standardization, digitalisation and managing of road maintenance data, and to support maintenance priority rating and long-term planning analysis. Even if the greatest benefits are gradually obtained over time, the application of PMS has already allowed to gather positive experiences, increase quality standards, and establish good practices in several municipalities in central Italy. Thank you for your attention.